afternoon, ladies and gentlemen, and welcome to another in the series of our SETI Talks Colloquium series. And we have a wonderful talk lined up for you this afternoon about the TESS mission. In the meantime, just to introduce myself for those of you who don't know me, thank you very much. My name is Bill Diamond, CEO of the SETI Institute. I just wanted to let all of you know, all of our friends and followers, many of you of whom I see here week after week. This is the end of our calendar year and the end of the tax year, 2016. And like many nonprofit organizations, we have a fundraiser going on right now to raise money for important programs like this colloquium series that we put on free of charge to the public, and we make the YouTube videos of this colloquium series available online on our YouTube channel, which has now about 400 of these lectures. And so you're always welcome and encouraged to go and peruse that inventory. There's quite an amazing array of wonderful talks. But if you'd keep us in mind as you think about your year-end giving and your year-end philanthropy to nonprofit organizations that do meaningful work, such as the Institute, in terms of our science and our education and our outreach, I'd be most grateful. You can do that quite easily by visiting our website online at SETI.org. And with that, I'll turn the mic over to Frank to introduce our speaker. Frank, thanks.
Hi. Good afternoon, and thank you for being here. So my name is Frank Marches. I'm a researcher at the SETI Institute, and today I'm going to be the host of this colloquium series. So let me introduce you to our speaker, Dr. George Ricker. He's the director of the Detector Laboratory and senior research scientist in the MIT Kavli Institute for Astrophysics and Space Research. He received his undergraduate degrees from MIT in physics, obtaining his master in astronomy from Yale University, and then went back to MIT for a PhD in physics. So most of us astronomers knows George for his research and interest, focusing essentially on the development of new solid-state photon detectors, CCDs and so on. And he's also a pioneer in the development of small, inexpensive, state-of-the-art satellites for astronomical missions. So I'm not going to give you a long list of all the missions he has been involved so far, but going to mention one of them because I kind of heard about it when I was a student, called HETI. We French people call it HET, but it's High Energy Transient Explorer, which was a small satellite incorporating instruments from France, Japan, and United States, which was launched in 2000 and was operating successfully for 6 years. So this instrument was designed to basically search for gamma ray burst. So Dr. Ricker has supervised a lot of theses, 11 in total. He's also involved with the École nationale supérieure de l'aéronautique et de l'espace in France. And I'm mentioning this because I know that they are watching those videos, those students over there at SuperEarths, so hi. And so he's currently serves as the Integrated Research Opportunity Program Coordinator for the MIT Kavli Institute. So if there is any student here who would like to go to MIT, this is the right person to talk to. But today, George is going to, who is a PI of the Transiting Exoplanet Sky Survey called TESS Explorer Mission, which is scheduled for launch in late 2017. We'll talk about this mission and describe to us the potential of this mission to search for exoplanets. Please join me in welcoming George Ricker.
It's a real pleasure to be here with you today, and I have a lot of fond memories of extensive time that I've spent in Mountain View in prior activities that we've had associated with TESS. And you'll see as I talk today about how some of these items have turned out both historically and in the current plans for the HETI mission. So the basic idea between our approaches to TESS is following on with the types of activities that were pioneered by the Kepler mission to actually bring a focus onto finding Earth-sized planets. And in fact, if we take what we currently know, partly from the Kepler mission, many of these planets you would expect to be associated with so-called red dwarfs or M dwarfs. These are stars that are a lot cooler than the Sun, somewhat smaller. They're the most common type of star in the solar neighborhood. 70% plus of the stars that we know of are such red dwarfs. The other thing is that we also know that, and this again is from the information that we got from the Kepler mission, that planets orbiting binary stars are actually quite common. And in fact, an entire new class of planet called a SuperEarth, which was predicted before the launch of Kepler. And these are planets that could be either water worlds, which this depicts, or Earths that are, or planets that are also partly rocky. They're somewhat larger than the Earth, but it's a category that we just don't happen to have one of these orbiting the Sun as part of our solar system. But basically the idea is that TESS would be able to unlock the secrets of these nearby planets, and so that the mission TESS itself is devoted to actually providing an optimized complement of instruments and investigations that would find these types of exoplanets. TESS is also considered to be a bridge to the future. Kepler made enormous contributions toward opening up this, this area of investigation. The James Webb Space Telescope, which is supposed to launch in 2018, will carry on this. And we've also designed TESS in such a way that it will provide a linkage to JWST and future missions as well that NASA and Europe and other space agencies around the world are going to put forward for this exciting new area of astronomy. In fact, one of the questions that JWST is encountering is where are the best places to point the telescope? And TESS is really intended in large part to answer that. And this actual image is about the right size. So JWST is a 6.5 meter telescope. TESS is really quite small, but yet with the large fields of view that it has and its ability to localize stars in that actually have transiting planets, it's the ideal combination in ways that I'll describe a little bit later. Now, many of you know what a transit is, but I'll just mention in at least quickly what it means. It's basically a condition in astronomy in which you've got a star, quite distant in many cases from the Earth, in which the orbital plane of any planets that it has orbiting around it just happen to lie along our line of sight. And this animation actually shows one such condition in which you then have a dip in light that has this characteristic box shape with an ingress and an egress as the planet actually crosses the face of its host star. Now this dip, this is actually quite large, but in fact these transit depths for many of the objects that we're going to be looking for are less than 100 parts per million. So this requires exquisite photometry in order to carry out these discoveries. And the physics that you can learn from these, from this very simple method of just the ratio of the area of the planet projected against its host star, in the primary eclipse, you can measure the size of the planet just by simple geometry. But in addition, you can also look for the signature of molecules in the atmosphere of the planet that are projected by the light from the host star passing through that atmosphere on its way toward us. And then you will also see, and people had sharp eyes would have noticed it before, that when you're out of transit, you'd see the things that look like the gibbous moon does, and you can find out a lot about the thermal properties of the planet from looking at those shapes and the exact shape that the light curves have as a function of phase. And finally, in the secondary eclipse, when it goes behind its host star, you can basically chop away the thermal radiation and tell the difference between thermal radiation due to the face-on planet and that of its host star. So there's a lot of information from an extremely simple measurement that you can have from transits. So to think about why we actually put TESS in the shape that it has and how the history of it worked, this is a sort of a brief history. Originally, now it's been 10 years ago, we thought about doing a very simple mission in the same way that we did HEDI 2, which is what Frank had referred to as a very small satellite. Based on what we learned from that, we thought we could do it as a privately funded small mission. And the Kavli Foundation and here locally, Google was very good about providing seed funding for this, and we sought private donors through MIT. And this looked like it was really going to happen. And then came 2007, and a lot of the private donors didn't have quite the resources that they thought they would have. So we had to restructure this as a potential mission of opportunity, which is a category of small mission that NASA had. And then in the process of our working on this program with our colleagues here at NASA Ames, it became clear that the selection of missions that were anticipated by NASA in the 2007-2008 meant that a small explorer, so-called SMEX, might be a way for us to carry out the mission. And with a very short lead time, less than 2 months, we hurriedly put together a proposal, and we were actually selected for a Phase A. We beat out 30 other missions, but we weren't selected for flight. So at that point, we said, okay, we'll try again. And in 2010, we reproposed TESS as a full explorer. And this time we were selected for Phase A, and we were also selected for a full mission implementation in 2013. And the program has been progressing, and I'll show you some of the hardware that we put together with a launch that's supposed to occur in late next year or perhaps a little later. But one of the other things that happened is that as we progressed through this, the costs started to grow because, you know, when you go down through this sequence, the requirements and the oversight grow, and so this is a necessary consequence for it. But still, this is considered to be a relatively inexpensive mission by NASA's standards. So the evolution of TESS occurred in another way, too. When we had it as a small mission like HEDI 2, we had 9 cameras on it with smaller fields of view to cover the sky. And then in 2010, in the first implementation we had, it had gone to 6 cameras. The cost had gone up, the number of cameras had gone down. And then finally, in the form that it's been selected now, the cameras have, the number has dropped to 4. But to be in all fairness, the properties of the cameras have changed in dramatic ways as well. So the goal that we've settled for TESS is basically to discover the best approximately 1,000 small planets. And these are planets that are rocky, water worlds, and potentially they're habitable planets. But basically the fact that that they're best means that they're associated with bright host stars, and that there's a real opportunity with instrumentation that's either available now for ground-based use or for facilities like JWST to measure the mass and atmospheric properties. So this is the area that we're really focusing on, and in order to do this, we want to carry out a large area survey, essentially the whole sky, looking for sunlight stars that are as bright as second magnitude, you know, readily visible eye stars, down to about 12th magnitude, and also this class of M dwarfs that are referred to earlier out to approximately 200 light years or so. But also this all-sky observation means that we'll be able to look at a selected group of target stars with a short cadence of about 2 minutes, but more than 10 times as many stars, 100 times, in fact, stars at about a 30-minute cadence. So, how do you do this? The point of comparison here is Kepler, and so how do you improve over in these properties over what Kepler was able to do? And basically, the idea of going for brighter stars, we designed the mission in two ways to solve that. First of all, we increase the solid angle coverage, so it's essentially all sky. Well, that gets us about a factor of 400. And as we all know, when you go out to the night sky, most of the bright stars are fairly uniformly distributed around the sky, and that's a function of the fact that you have to go some distance from the sun inward toward the plane of our galaxy, either toward the galactic center or anti-center or along an arm, before you see the clumping down that constitutes galactic structure. Within 100 parsecs or so, there's a fairly uniform distribution. The other thing is that for these bright stars, you generally know approximately how distant they are, so we can actually select the ones that are within about 100 light years, and then the 1/r² dependence means that they should be about 100 times brighter on average. So if you then say, well, what does this gain for you? This is a plot that shows planet radius and host star magnitude along this axis, and the blue dots are those associated with Kepler. The red dots are associated with the TESS stars, and here you are with the naked eye, binoculars, or a modest-sized telescope in this range. And so basically, this is a logarithmic scale. This is about a factor of 100. So these early simulations that we did showed that this was something that was probably going to work, with the TESS planets being easy to follow up, and the Kepler ones less so. And then the other thing is this band right in through here, this box area in yellow, is where the Earths and SuperEarths would lie, and you can see there's a preponderance of red dots in this section. So that was what the mission was and is focusing on. The other thing that we were able to do was we were able to optimize the pass bands that would permit us to find more M dwarfs. The red trace, right, this is wavelength in nanometers along here, and then this is this is a measure of the quantum efficiency or the instrumental efficiency of the mission as a whole, the cameras. So this is an M dwarf along here, and then this is a G star like the sun. And you can see we by emphasizing the region from 600 nanometers to to a little beyond 1 micron, we have more flux from these red stars. So that's the way it's arranged. And then the other thing is that by the solid angle, we'll be able to optimization that we made, we'll be able to find about 100 times as many stars to look at. What I'd like to share with you now is a simulation that gives a little bit, both qualitatively but also quantitatively, an assessment of what this actually means. Now, this is a simulation that a former postdoc in our group, Zach Berta Thompson, put together that shows the projection of potential host stars onto the plane of the Earth's orbit around the sun. And the dots that you'll see come in indicate that you're looking at systems that were discovered by non-Kepler missions. So some of these are radio velocity discovered systems. Kepler will be in gray, and the predicted TESS planets are going to be this orange salmon colored. And if you see a 5-pointed star, that means they're potentially habitable, and there's also going to be an indication of the temperature. So if I let this run, here's where we are. This is going out to about 6 parsecs, and here's a potential candidate that is first arrives. This, there's some uncertainty, but it's plausible to expect that there may be a relatively nearby system. In fact, since we put the simulation together, many people know that Proxima Centauri has been found to have a habitable planet, potentially in a region where liquid water could exist. and it's only about this far out, around just a little over 1.3 parsecs. So if I let this run a bit further, you see as these rings go further and further out, there's a fair number of orange stars that come in, and then here's a Kepler candidate that comes in at this point, and you can see the density of points is such that there's a lot out there that we can expect to discover. And then if I let it run a little further, so now we're out to around 100 parsecs. You see this spray of points extending off to the upper left, and of course that's the wealth that Kepler has been able to provide, but many of these are fainter and they're going to be more challenging to follow up, whereas the TESS ones are close in and will be much easier for follow-on observations. Okay, now I'd like to share a little bit. I mean, we started this mission, we were selected for this mission back in 2013, so then, what have we been doing for the last 3 years? And I'd like to share with you some of the hardware that we've actually been able to produce. The CCDs that are associated with TESS, here is one such flight array. This was being inspected. The CCDs are each 2K by 4K, but we deliberately mask half of each CCD so that it can operate in what's called a Framestore mode, where you basically shift the charge that you're integrating, which is occurring in this black area. It appears black because the anti-reflection coating on the CCDs is optimized to work in the near infrared. So to your eye, it looks black. So the charge is actually shifted from this chip up into this store area, from this one this direction, from this one here, and this one there. And so that may, with the shift times that we have, we can reduce the smearing that occurs to of order 1%. The integration times are about 2,000 milliseconds, and this shift operation only takes about 20 milliseconds. So then we put this together. This is a camera that is fully integrated with not only the focal plane, but there's electronics associated with it. You can see some of the boards that were actually tested at the same time. And then so basically that was one system that we need. Well, we also need a lens, and so basically this is the TESS camera with the detector assembly here, and the CCDs are along in this area. And then we have a lens assembly that has, it's a 7-element aspheric, at least two of the lenses are aspheric, that has an extremely wide field of view, and it's also quite fast. It's f1.4, and a system like this had not really been designed before. At least that would not be able to operate at -75 with the sharpness of focus that we need. And then finally, we have to be aware of the fact that there may be scattered light, so there's a very extensive lens hood that we had to also design to be part of this. And so altogether, we've got this configuration here, 4 cameras, and they're arranged in this sort of canted mode in order to provide sky coverage that I'll come back to in a minute. So we've got 4 cameras, each has a 24 by 24 degree field of view. This is, in fact, the first flight camera undergoing a thermal vacuum test at MIT. So you can see this is the front lens element here, and then as you work your way back, there's no lens hood present here. The focal plane is not visible, but it's where the transition from black to this bronze color occurs, and then the camera, the electronics are in the back, and this bit of plumbing is associated with a purge system that we have to have. And then this is when you're looking into the chamber, and you can see this greenish coat that's associated with the anti-reflection coatings in the lenses themselves. So there is visible light that comes into the system at 600 nanometers, but it turns out that we get this characteristic visible appearance for the lens. This is a large, this window allows us to bring in an artificial star pattern that we use to characterize the focal plane and the properties of the lenses. And in fact, the the size of the lenses and the overall assembly is such that we can test each flight system that we have and be assured that when it gets to orbit that we've tested the whole system end to end. And this is something we're really happy about. This gives you an idea of how small TESS actually is. This is a full-scale model, and the part that's in silver below is where the spacecraft actually resides. There's a Ka-band dish that points to Earth and provides data recovery, and the cameras live in this little inverted quadrilateral structure above this. So this is it's about 1.5 meters high, and it weighs a little less than 400 kilograms, including the propulsion system that's associated with it. So we're going to be launching on a Falcon 9, and so there were a lot of testing stages that were involved with a mechanical mock-up of the spacecraft, and then this is just the structure that encloses the sunshade assembly, and the cameras would be in there. They weren't part of this test. This was basically a mechanical model test to make sure that all the parts were going to play together. The spacecraft itself is under construction right now at Orbital ATK in Dulles, Virginia, and it's a hexagonal structure, and the wiring and component emplacement is all taking place. And we plan, after this is complete, sometime in the spring, in the April-May timeframe, to bring the cameras and integrate them into this assembly. Now, as I said before, the Falcon 9 is the rocket that we're going to be flying on. It has had problems from time to time, but we're pretty confident that they'll get it sorted out. But it's a very interesting choice if you look at where TESS really fits in on this. It's not exactly optimized for this, but there are reasons that it is the best choice, and some of it's related to the lowest bidder. So that's what we had to work with. I'm sure it'll be okay by the time we need it. So the sky mapping strategy for TESS is something I'd like to discuss with you and show you some animations that are related to it. As I mentioned before, there are 4 cameras, and they have these canted fields of view. So when the satellite is in orbit, the sun is actually coming from the left, and the fields of view of the camera are splayed out from the ecliptic up to the ecliptic pole. So you end up with a composite field of view that's 24 degrees by 96 degrees long. So that's about 2,300 square degrees. So that's approximately 20 times the field of view that Kepler had. And then we basically tiled together these successive measurements that are made at 27-day increments. And then we first do 1/2 the sky in the first year, and then the other half in the second year. And you see that there are these areas of concentration that are deliberately chosen to provide coverage for the JWST continuous viewing zone. And so when we're done, we end up with a sky map that looks like this: 13 segments in the north, 13 segments in the south, and there's a gap of about 12 degrees along the ecliptic, because we wanted to make sure that we could provide extensive coverage. And in fact, if you just tip it over a little bit and look at where the ecliptic pole is here, we have about almost a year of coverage in an area that fully encompasses the continuous viewing zone. And in fact, the area shown on the cap with the dashed line is where we can observe for more than 200 days a year with JWST. Because if you're doing follow-up observations of transits with JWST, you want to make sure that you don't restrict the operation of that facility, so you make sure that you find targets that are really optimally placed for JWST as well. Now, in order to do this, the part I didn't tell you about when I showed you that first image is that if you try to do a mission like TESS close to the Earth, you've got basically 2 pi behind you of sky that you can't really look at. Also, you're going in and out of orbit night and day, and it's very complicated to operate it. There's thermal problems and all that. So what we decided to do was to change the mission in a way that made it possible for us to observe pretty much continuously, and that's what this animation is going to show. We basically launch from Cape Canaveral, and we launch into a highly eccentric orbit that goes out about 2/3 of the way to the moon, and then we come back around. So this is a transfer or phasing orbit that we go. Then we give it a little bit of a boost and come back at a higher altitude. It looks like this is a little choppy, but I think you can get the picture. So then in that last phase, we actually are out at the lunar distance. We do a lunar flyby that actually tips the orbit down by about 37 degrees or so. It depends on exactly when we launch, and then you tip it up, and then you do another orbit phase adjust here, and then ultimately you settle into an orbit that is 59 RE by 17 Earth radius, and in this way the orbital period turns out to be half the period of the lunar month. And you might wonder, well, what's the significance of that? Okay, but first of all, I'll come back to that in a minute. But one of the things I'd like to show you is that a little bit more quantitatively than what I showed you is exactly how the observations work in this inclined orbit that's highly eccentric, and this is what this shows. Now, the dates that are chosen here from May of 2018 to August, this 3.5 months, it would be the early phases of the TESS mission. And so what you end up seeing is the following. Here's TESS, here's the moon the Earth rather twirling around here, and the moon is going around in this area. And these are the 4 fields of view. And if your eyes are quick, you'll see that there's an a pointing adjustment that's made. There was one every 2 orbits. And so we basically established that cadence that was shown in that static representation that I gave you before. So this goes on, and there's other complications that occur, like occasionally the sun will come through, and if you're oriented correctly, you don't have problems with that. But TESS always looks in the anti-sun direction. So to sort of see why we're going to all this trouble, one of the things that we found by doing a little bit of orbital mechanics on the mission is that if you were to go into this type of an orbit, which is a resonance orbit, so-called 2-to-1 resonance or a p/2 orbit, and you were to launch into, you were not careful about the choice of inclination and your choice of phasing, almost always you would crash into the moon within 2 years. It's a very unstable configuration, so that's not desirable, so we chose not to do that. But on the other hand, it's a great orbit because of the fact that you're well away from both the Earth and the moon. And so the way we get around this is the following. You can see there's the moon, and there's TESS, and there's the Earth. And if I stop it right here, you'll see we've got a configuration where this is TESS, this is the Earth, and this is the moon, and this is roughly a 90-degree angle. So basically what happens, this configuration occurs both the way that I've shown it here, and if you let the animation run a little bit more, what happens is that 2 weeks later, you'll get the same 90-degree conjunction that occurs. And it turns out that in one case, what's happening is the moon is tugging the orbit one direction for 2 weeks, and then the other direction for the other remaining 2 weeks, and it basically stabilizes the orbits. There's no propellant, nothing required. You get into this, it's not really stable, it's metastable, but it's metastable on periods of decades. So this is an orbit that really hadn't been used before, and the reason that we chose it is that it greatly simplified the operation of the mission, and it was also something that we could forward within the cost cap that the mission has. So you get these 7 major advantages. You can have long observations, 300 hours per orbit, because that's approximately what you get. The environment is very stable. You don't have to use anything other than passive control. The Earth-Moon stray light is a lot less than it would be in a low Earth orbit, 1,000,000 times less so. Radiation is not a problem because when you come in at perigee, you're above 100,000 kilometers, and at that level, you're above both the trapped proton and trapped electron belts. And also, this was not obvious when we did the calculations. It turns out that this is something that you can achieve as far as this launch configuration, several days per lunar month, so you don't have the kind of once every 2 years or so that you get for some of the planetary missions. And the other thing is, since you're above the atmosphere, you're well away from the Earth, gravity gradient effects are not significant. But this is another really big deal, is because you're coming in fairly close to the Earth, you're able to run high data rates, 100 megabits per second. And we can, in fact, run even higher than that, except that's the maximum rate that the Deep Space Network will actually provide for missions that are operating at Ka band. And that's a 23 dB gain factor over what you would get from an Earth-Moon Earth-Sun L2 orbit. So there's lots of reasons to do this. In fact, when we first proposed this, there was a lot of consternation about this, and we had to do a lot of work to prove that it was plausible. And there's several papers that we've used to describe the mission here. This is a little bit of a cartoon that shows the data flow for TESS. The cameras are integrating continuously, and with 2-second full-frame images, and that's what this part just shows them all being stacked up. And then this is the processing that's occurring on board, in which we're extracting postage stamps in the same way that Kepler did from these full-frame images. And then these are all around pre-selected locations, and we do about 15,000 stars per orbit, and then they're stored in a solid-state recorder that's part of the satellite. And then in parallel, we're also stacking these images on board in 30-minute full-frame increments, and then we get 600 of these from each of the cameras during the 14-day orbit. And again, they're stored for transmission. And then in addition, we phase the frame times in the 4 cameras, so they're actually slightly askew by a half a second, and that provides frequent updates in the quaternions that are needed for guiding the satellite. And so that's the other thing, is that so the satellite itself locks onto a field that's determined by the science instrument itself. So that's another thing that simplifies the operation of the satellite. Okay, well, in the time related, I'm going to show you some of the yield simulations that we've got, and these will be based on model simulations from catalogs of known stars. So this is what we expect to see in a 1 square degree of the sky, and the little green rectangles are the roughly 10 by 10 pixel areas that are associated with a given star. And so this is 1 degree along this axis, 1 degree along that axis. And these are a priori known interesting stars that we're actually going to put in a catalog. Then here's that green square up in this upper right-hand corner. This is what a single CCD will see in this simulation. So you see there's a star cluster here, and there's evidence along through here of absorption from interstellar gas or dust, rather, along this area. And then if I zoom out a little bit further, this is the 24-degree field of view that you get from one camera. There's that little 1 square degree thing, and then we actually put in defects associated with the CCD for the simulation. And just to give you a feeling for how much this actually means, we're going to, in the full survey, we expect to have 30 million discernible objects in these images, of which about 20 million will be stars and the other 10 will be non-stellar objects, primarily galaxies. And then to give you an idea of how big this really is, this is what Orion looks like projected into this field. Okay, now if you then say, okay, well, where are the planets that we would expect to detect, and what are the features that you can see in it? Well, this plot is a plot of the TESS detections from the 2-year mission in ecliptic coordinates. So in this set of coordinates, this is the plane of the solar system, the ecliptic itself, and this is the north ecliptic pole and the south ecliptic pole. And what you can see is, just as we designed the survey, there's a concentration of objects in the ecliptic pole regions. And there's some other features that you see in this. Here's the area that we do not look at in the primary mission. We hope to fix that in an extended mission. And then there's another area along here where no detections are shown, and that's primarily because that's the plane of the galaxy, and we think that it'll be too confused for us to make discrete determinations of transits in there, but we're not sure. Anyway, so the red is the 200,000 pre-selected stars, and shown in this sort of little fuzzy underlay are the 20 million stars that will come out of the full-frame images. And so this is the location of the Kepler field in this at the edge of the galactic plane in the northern ecliptic hemisphere. So the yield if you take the planets that are actually in that simulation and then break them down by the size that they actually have, here are Earths, SuperEarths, sub-Neptunes, and giants. So that's a characterization based on the radius of the planet. So we have altogether, this is a log scale actually in terms of the number of detections, so keep that in mind. And then we've got 500 planets that are in this category that are smaller than 2 Earth radius, and these are going to be ones for which mass measurements are hopefully practical, and we can resolve whether they're rocky planets or Earth or water worlds, or exactly what is the transition depending on the composition that they actually have. And then for the planets that are in this category here together, these are planets for which atmospheric studies by JWST would be possible. Possibly a few of the super-Earths will fall into this category, but many of the sub-Neptunes actually will. And then finally, there's this more than 10,000 giants that will be detected that can be used for evolutionary studies of hot Saturns and Jupiters in the future. So one question that always comes up is, okay, what about test planets in the habitable zone? This is a figure, it's a little complicated. The x-axis on this is relative insolation. That is, it's the amount of energy that these planets are going to receive compared to 1, which is what the Earth receives from the Sun at our orbital distance of 1 AU. So the bounds that are shown in this plot say you could go to something that had twice the solar insolation to something that's 2/10 of the solar insolation. This is one model for how you would sort of stretch the boundaries of what a habitable zone could be. And then you can see, first of all, that these are concentrated primarily toward cooler stars. The Sun is way up here. These stars are all M dwarfs that are in this section with temperatures lower than 3,500 Kelvin. And then finally, if you say, okay, this is the boundary of a more conservative boundary of where you would actually have the habitable zone, then you find that there's something like 10 or so really nice planets that there will be very little question as to whether they're in the habitable zone or not. So the way we actually do the measurement, as I think I indicated at the beginning, with transits alone, you cannot establish the mass of the planet. You can only determine its apparent area and projection, and if it's spherical, that means its volume. So in order to determine the radius, in order to determine the mass, you need another methodology. Now, one convenient way of doing this that we've actually put in place measurements within the team is to make radial velocity measurements, basically the Doppler tugging back and forth that occurs when the planet actually goes around its host star. It moves the planet, it moves the star back and forth it changes the Doppler effect from 300,000 kilometers a second down to something like a meter per second. So it's a really tiny effect, but ground-based instruments are able to make these kinds of measurements. And so in the case of TESS, basically this little inverted funnel shows we start out with light curves from about 200,000 stars. This is just done for the case of the postage stamps. This is all spacecraft data that comes down, and we've predicted that we'll have transit-like signals for about 300,000 stars in that collection. And then this information gets delivered to an archive in 4 to 6 months for other people to work with as they wish. And then everything from here on down is associated with work primarily by ground-based telescopes for screening these objects. And so when we actually take ground-based imaging at sort of 1 arc-second imaging, you can determine whether some of these are binary systems, eclipsing binaries, or not eclipsing binaries, but accidental binaries that you have. And so the majority of the transit-like signals will probably survive that test. And these are the facilities that we've lined up already to help us in that task. And then finally, we will do reconnaissance spectroscopy, which is if you've got an eclipsing binary system, that is 2 stars and not a star and a planet, typically the radial velocity change that you'll get for that will be in the hundreds of meters per second to a few kilometers per second. And so you can tell the difference between that and the few meters per second radial velocity shift that you'll get for a planet. So that's what we actually screen to make sure that we're getting rid of eclipsing binaries. And then finally, when we know we've got something that we want to see, is it an Earth-sized planet or whatever, these really stable instruments like this this is a European instrument, HARPS. It's in the southern hemisphere, and there's another instrument like this on a telescope in the northern hemisphere. So we think that will select some of these and make those characterizations. So for this validation step, we're going to select about 6%. And then the requirement on the mission itself that we agreed to with NASA is that as part of our level 1 requirement, which means if you reach this point, everybody's happy, your mission is a success, is we have to be able to measure 50 masses out of that. But that means that there's 94% or so of these that are available for community follow-up, and there's going to be a lot of things that can be done in this area by amateurs, university telescopes, other facilities. This last part is really challenging, but there's a lot of work that can be done to look for these candidates in the way that reconnaissance spectroscopy is being carried out. The other thing is that TESS is, because of what I told you earlier, the orbit's very stable. One of the things that we've been talking about are ways that we can actually move the spacecraft around and carry out surveys in subsequent years, and that's what this actually shows, different scenarios that Luke Buma, who's a graduate student in the program, has been considering. This is something that would happen in years 3 and 4 or possibly even later. NASA has actually established, even though we haven't launched already, a guest investigator program for TESS. It's already funded, and people can ask for new targets that are part of this. The spacecraft isn't going to do anything different. It's just that these are going to be objects that we'll pay a special attention to. And so the funding for that is $2.5 million a year, And there's going to be a call for proposals on this in early next year. So this is a website that has additional information on that. So the timeline for TESS is shown here. Here we are at the end of 2016. We're in the midst of flight hardware and software and testing. Around this period of time, we'll be testing the integrated observatory with the spacecraft and all the instruments. The launch should occur near the end of calendar 2017, or maybe a little bit later than that. Then we do the southern hemisphere, the northern hemisphere, and then at this point, we'll see what happens in terms of an extended mission. So the other thing I wanted to mention to this group is that there are research scientist positions associated with the TESS team, and so we would invite anyone in the audience or people that you know who would be interested in these to actually respond to the ad postings that we have on these. These positions are immediately available, and we'd be happy to receive expressions of interest for these areas. So these are the takeaways from the mission. I talked a little bit about JWST and how that's important, but the Giant Magellan Telescope, the 30-meter telescope, and the European extremely large telescope, which is 40 meters, these are going to be equipped to actually follow up these transiting systems with atmospheric spectroscopy, so they're very interested in the targets that we're going to find. The launch date is what the launch date is going to be. We can operate in principle for an extended period, and I think this is the key point, is that these are really going to be the best small planet targets for radio velocity measurements, in this decade and in decades to come. It's because of the nature of the way that the survey has been designed. So thank you, and I'd be happy to respond to questions.
Okay, the floor is open for questions.
So thank you for that talk. That's exciting. We look forward to the launch next year.
Yeah.
A question, for any given star that is targeted for observation, how long does the instrument observe that single star, and then what is the rep rate, or what is the frequency of revisiting that star in terms of the image repetitions?
Well, it depends on the ecliptic latitude that field has. If it's the shortest period of time is the 28 days associated with 2 orbits, and then as you move further up toward the ecliptic pole, that number grows. So with the overlaps there, it's almost an entire year. Basically, when we would come back to that field again would depend on what happens in the extended mission scenario, because the goal is to observe as much of the sky according to this mapping strategy that we actually figured out in the baseline 2-year mission. And so we hope that it will be possible to cover additional scenarios, and also it'll depend a little bit in terms of choosing which of those 6 or other extended mission scenarios. It'll depend a little bit on what we find and what makes sense, and how effective the follow-up is from the resources that people have in place already.
Hi, over here. So given that your extended mission runs way past the JWST launch date, I understand TESS's purpose of finding candidates for JWST to look at, but once both, in the optimistic scenario, both telescopes are flying and looking at things, how do you see feedback? Do you see any feedback coming from JWST for something to test to look at and back and forth? Are there different sensitivities to light frequencies allow for complementary observations, or how do you see those 2 telescope teams interacting?
Well, as far as the interaction for TESS providing targets, I think that was clear from what I described. The other way around is a very interesting question, because what can happen is that if JWST makes an observation for a transit, you really only want to make the observation of that transit when something is actually going on, because most of the time when the orbit of the planet is out of transit, it's just sort of sitting there, and you're looking at the sum of the optical light from both of them, which basically means you're just looking at the light from the star. So those transit durations are typically an hour, and it's for habitable zone systems. We're talking about things that maybe you get a transit every 10 or 20 days. And if that's the case, you don't want JWST to go staring at that area and then nothing is happening. So what you could do for some of the high priority candidates is make a revisit to basically refresh your understanding of when the transits are actually occurring. So that's one way in which what you ask would be an interaction.
A spacecraft engineering question. So you use the science instruments for attitude control? You determine attitude
Right.
for attitude? Okay, so there's no other star tracker on board?
There is actually a star tracker. There's it's made by a group called the Danish Space Research Institute. It's a star tracker that basically the way the system operates is that star tracker has a precision of 5 or 10 arc seconds, and the way the control loop actually operates is once you have the satellite itself provides basic information the spacecraft provides basic information on where we are, and then what happens is that once you get within about an arc minute of what your target field is supposed to look at, then the star tracker on the spacecraft hands over control to the information that's acquired from the science cameras, and then they basically lock in to arc second accuracy on the field that you want to settle to, and the pixel size on the science instruments is actually rather coarse, but because we have such a large field of view, we can have 100 plus stars, so that means we reduce by the square root of 100 the localization. So it's a 2 or 3 step process that's involved.
Okay, and then you're talking about a 20-year mission. Are there consumables on board, like momentum dump propellants that limit that?
Yes, we're flying a total of 44 kilograms of hydrazine. Most of that's used in the phasing orbits to get us to where we want to be for the lunar encounter and for the adjustments that are made after that. But the margin that's left over from that is more than 10 kilograms. And we've estimated that you do need propellant when you do the momentum dumps. That'll primarily, and you also, when you steer the antenna, steer the Ka-band dish to point at the DSN, that may or may not take propellant depending on whether you stay within the linear region for the momentum wheels. And then what you basically do at that point, though clearly you will have to change momentum, and we've calculated that that's going to take, we'll have to manage momentum. That'll probably take a few grams of hydrazine per year. So we would have an enormous amount. The spacecraft is balanced. It's got 2 solar panels. It's largely symmetric. There's no atmospheric drag or anything like that. So the estimates that we've made are, it may be 10 grams per year, but it's a tiny amount compared to the 10 kilograms that we've actually got. So hopefully that'll work.
One other spacecraft question. Who's your reaction wheel vendor?
It's not the same one that was used by Kepler. The vendor's name escapes me right this minute, but it's one that's been used extensively before, and they're not the same wheels. I could find out and tell you later, but.
Oh, yeah. I have a questions about the pipeline. You mentioned there will be a guest visitor, guest investigation mode.
Right.
What's your strategy for transient events such as asteroids and supernovae and so on? You
Well,
gonna store the data? Or?
Yeah, the data for that, we're still exploring exactly how we're going to do that, but for the transient events as opposed to transit events, we've estimated that if the variation in brightness is of order 10%, it's like a tenth of a magnitude. It should be very easy to pick those out in the full frame imaging pipeline. And if they occur at a very early stage, we would basically make that data available quickly to the community. There's a network system that we use for the HEDI 2 satellite called GCN. It's operated at Goddard Space Flight Center, and we've got the plumbing to send alerts through that, and that's what I think we would do.
I'm wondering why the thing wasn't designed to capture the entire sky and miss the ecliptic, just barely missing most of the ecliptic. Is there a trade-off there?
There was definitely a trade-off there, and I'm smiling because this was a very interesting situation that we had. Originally, the design was that the cameras would have fields of view of 22.5 degrees when we were working on it in phase A, so 4 times 22.5 is 90 degrees. And then we would have one of the cameras would just come tangent right to the ecliptic pole, and the fourth camera would come right down to the ecliptic. So when we studied that a little bit more, we said, that's just not good. You'd really like to have one camera that's more or less sitting on top of the ecliptic pole for that entire year that you're there, because that's such a wonderful sweet spot for JWST. So we try to make the fields of view larger and control the aberrations in the optics. And it turned out the largest number we could get to was 24 degrees. When we went from 24 degrees to 25 degrees, the optical design just really degraded very rapidly. So that's essentially all we could manage. I tried for 27 degrees, and the engineers struggled with it for about 2 months, and they said, nope, not going to work. Then we backed off to 25 degrees, and finally 24 degrees was what we had. But that's a very interesting question, and something that I wish we had been able to make them a little bit bigger. But it's we've got 7 elements in the optical system. To do something like that, we would probably have gone to 8 or 9 or even 10 elements. And the real problem, the lenses start to get heavier, and if we had known at that point that we were going to be on this monster rocket, which was not selected until a year after we had completed phase A, then there may have been other ways, flying more cameras, changing the optical design, and in other ways that we were constrained by that environment. If you noticed, all those cameras being clustered together, and then this tiny little satellite inside that monster fairing, if we had known that we were going to be in that monster fairing, we would have really spread things out, and it would have made everybody a lot happier. But the requirement at the time that we proposed for TESS was that it fit within the confines of a fairing that was made for another rocket called a Taurus, which Orbital Sciences flew. And that was the one that, this was before the Falcon 9 was really being considered, and an Atlas V was far too expensive, so we had to deal with that situation. And once we had that design in place to say, oh, well, let's make everything bigger and all that, well, we were too far down the line for that to work.
How many transits of a given planet will you typically detect? And I assume that'll vary a lot.
It'll vary quite a lot. For habitable zone planets around mid to late M dwarfs, for stars that have temperatures of less than 3,000 Kelvin, typically we'll get 2 or 3 transits during that observation cycle. So the transits will occur every, as I said before, 10 to 20 days. So for the systems that are in the ecliptic pole, we'll get a fairly large number of transits because as we step around, we'll be looking at that field pretty much continuously. So we'll get lots and lots of transits there. As you move down toward the ecliptic, you get fewer and fewer, but typically 2 or 3. But there will also be systems, around G2 stars like the Earth around the Sun. Once a year, well, you'll have a very small number of those at low ecliptic latitudes.
Okay, thank you. Thank you, George. As a token of our appreciation for coming all the way here, you get this amazing mug for you drink coffee.
That's wonderful. Thank you.
Thank you for your talks, and good luck with the launch, and see you in 2 years maybe with the first result
Great.
of TESS.
Thank
Thanks
you.
a lot.
Right. Thank you. Thanks.